Out there, in the cold, silent reaches of our solar system, beyond the orbits of Neptune and Pluto, drifts a world so strange and so little understood that even its name sounds like a whisper from the unknown Varuna. Discovered in the year 2000, this distant dwarf planet has puzzled astronomers from the moment it first blinked into view, not just because of where it is, but because of what it refuses to tell us. Imagine a place where the rules of the cosmos seem to bend, where light takes hours to reach, and where mysteries pile upon mysteries, 25 of them to be exact. That's Varuna, a world that shouldn't be as enigmatic as it is, and yet here we are staring into the void, wondering what secrets it's hiding. What makes Varuna so fascinating isn't just its distance over 4 billion miles from the Sun, but the way it defies expectations. Most dwarf planets quietly orbit, content to be frozen relics of the early solar system. But Varuna, it spins faster than it should. Its surface reflects light in ways that don't quite add up. And then there's the shape, irregular, uneven, as if something colossal once struck it, leaving behind scars we can't yet decipher. Every time scientists think they've pinned it down, Varuna throws another curveball, another question without an answer. It's maddening, it's exhilarating, and it's precisely why we can't look away. This isn't just a story about a tiny world at the edge of everything. It's about the human hunger to uncover, to explore, to stand at the frontier of knowledge and peer into the dark. Because for every mystery Varuna holds its bizarre rotation, its puzzling composition, the strange way it interacts with the faint glow of distant starlight, there's a chance for discovery, for that moment when the universe finally whispers back. So buckle up, we're about to dive into the 25 greatest enigmas of Varuna, each one stranger than the last, each one pulling us deeper into the unknown. The questions are vast, the answers few, but the journey, that's where the magic happens. Varuna doesn't just drift in the outer darkness, it dances. While most objects in the Kuiper Belt follow orderly, near circular orbits around the Sun, Varuna cuts through space like a rogue comet, tracing a path so stretched and tilted it leaves astronomers scratching their heads. Its orbit isn't just elliptical, it's wildly so, swinging from a distant, sluggish crawl at its farthest point to a startling burst of speed as it hurtles closer to the Sun. And then there's the tilt. Unlike the flat, predictable plane where planets like Neptune glide, Varuna's orbit is cocked at an angle, as if some ancient cosmic hand gave it a shove and sent it spinning off kilter. So what could have thrown Varuna so violently off course? One leading theory points to Neptune's gravitational pull. Billions of years ago, as the giant planet migrated outward, its gravity might have slingshotted Varuna into this bizarre trajectory, a celestial billiard shot frozen in time. But not everyone's convinced. Some researchers argue Varuna's path is too extreme for even Neptune's influence, suggesting something far more dramatic, a collision. Imagine another massive Kuiper Belt object slamming into Varuna long ago, knocking it askew like a top struck mid-spin. The impact could have left behind more than just a crooked orbit. It might explain the dwarf planet's odd shape and frantic rotation too. Yet the puzzle deepens when you realize Varuna isn't alone. A handful of other distant objects share similarly skewed orbits, hinting at a larger, untold story. Could these outliers be survivors of a chaotic era when the outer solar system was a demolition derby of clashing worlds? Or is there an unseen force, a hidden planet perhaps tugging at them from the shadows? Every answer only unspools more questions, and that's what makes Varuna's orbit more than just a quirk. It's a clue, a breadcrumb leading us back to the solar system's most violent, formative moments, and proof that even in the frozen quiet of deep space, nothing ever really sits still. Varuna doesn't just move through space, it whirls. While most objects its size take their time, lazily spinning once every dozen hours or more, Varuna completes a full rotation in less than 6. That's faster than Earth, faster than Mars, faster, in fact, than nearly any other known dwarf planet or Kuiper Belt object of its size. This breakneck spin isn't just unusual, it's downright perplexing. In the outer solar system, where everything moves at a glacial pace, Varuna behaves like it's had one too many cups of cosmic coffee. Speed like this isn't just a curiosity, it's a clue. For an object as large as Varuna, such rapid rotation should, by all rights, tear it apart. The centrifugal force alone ought to stretch its surface to the breaking point, reshaping it into a flattened ellipsoid or even ripping it into smaller pieces. And yet, Varuna holds itself together. So how does it defy physics? One possibility is that it's not a solid, rigid body at all. Instead, it might be more like a loosely packed snowball with a porous, rubble pile interior that flexes and absorbs the strain of its own spin. Think of it like a spinning pizza dough. If the dough is soft and malleable, it can stretch without tearing. Varuna's interior could be just as forgiving, a jumble of icy fragments held together by gravity's gentle grip. But there's another, more dramatic explanation, a colossal impact. Picture this: billions of years ago, another massive Kuiper Belt object slams into Varuna at just the right angle, delivering a glancing blow that sends it spinning like a top. The collision wouldn't just speed up its rotation. It could also explain the dwarf planet's irregular shape and the strange distribution of light and dark patches on its surface. Some scientists even speculate that Varuna might have once had a moon, torn away by that same violent encounter, leaving behind only the echoes of its presence in the planet's frantic twirl. What makes this mystery even more compelling is that Varuna isn't entirely alone. A handful of other distant objects, like Haumea, also spin unusually fast, hinting that whatever happened to Varuna might be part of a larger pattern in the outer solar system. Were these worlds all shaped by the same chaotic era of collisions, or is there some other unseen force at work, nudging them into these hyperactive states? Every new observation deepens the intrigue, turning Varuna's spin into more than just an oddity. It's a window into the solar system's most violent, transformative moments. One thing's for certain, Varuna's rotation isn't just a quirk. It's a fingerprint, a trace of something far bigger lurking in its past. And as we keep watching, measuring, and questioning, we might just find that the answers rewrite what we thought we knew about the frozen edges of our cosmic neighborhood. Varuna plays tricks with the light. Even from a distance of 4 billion miles, astronomers have noticed something peculiar. Its brightness doesn't behave the way it should. Most rotating objects in space show predictable patterns, dimming and brightening at regular intervals as different sides turn toward Earth. But Varuna, its flickers are erratic, almost unpredictable, as if someone is shining a cosmic spotlight on random patches of its surface. These fluctuations aren't just minor blips, they're significant enough to suggest dramatic variations in texture, composition, or even activity across its frozen exterior. So what's casting these shifting shadows? One leading possibility is stark contrasts in surface features, vast, dark regions sitting alongside highly reflective ice. Imagine a landscape where sprawling plains of pitch-black organic material, perhaps methane or carbon-rich compounds, stretch between gleaming stretches of fresh, bright ice. As Varuna spins, these starkly different terrains would catch the sunlight unevenly, creating the irregular brightness patterns we observe. It's not all speculation either. Similar features have been spotted on other Kuiper Belt objects, like Pluto's dark highlands or the mottled surface of Makemake. But Varuna's variations are more extreme, hinting at processes we haven't yet pinned down. Then there's the more tantalizing explanation, cryovolcanism. Picture geysers of slushy ice and ammonia erupting from Varuna's interior, spewing fresh, reflective material onto the surface in unpredictable bursts. Over time, these frosty eruptions could create patches of ultra-bright terrain, while older areas darken under eons of cosmic radiation. the idea isn't as far-fetched as it sounds. Moons like Europa and Enceladus have active ice volcanoes, and even distant Pluto shows signs of geological renewal. If Varuna harbors similar activity, it would rewrite our understanding of how dynamic these far-flung worlds truly are. Yet the plot thickens when we consider timing. Some of Varuna's brightness shifts don't sync up with its rotation at all. Instead of cycling predictably every 6 hours, they appear and vanish on their own schedule, almost like celestial Morse code. Could this be evidence of transient clouds of frozen gas hovering above the surface, briefly scattering sunlight before dissipating? Or perhaps it's something even stranger, like reflective dust kicked up by micrometeorite impacts or shifting ice dunes driven by subtle solar winds. No single theory quite fits all the data, leaving scientists to piece together clues from half a solar system away. What makes these flickers so fascinating isn't just the mystery, it's what they reveal about Varuna's hidden personality. A world this remote should be frozen in time, a silent relic of the solar system's infancy. But the longer we study it, the more it behaves like a place of change, even chaos. Whether through ancient scars, volatile ices, or forces we haven't yet imagined, Varuna refuses to sit still. And that's the real enigma, not just what's causing the light to dance, but what it's trying to tell us about the secrets buried beneath the ice. Here's the conundrum with Varuna's surface: it shouldn't exist, at least not like this. When astronomers first analyzed the faint light bouncing off this distant world, they expected to see the usual suspects: a bland coating of water ice mixed with rock, the standard fare for Kuiper Belt objects. But Varuna's spectral signature told a different story. Hidden in those shimmering reflections were the unmistakable fingerprints of methane, nitrogen, and complex organic molecules, ingredients far more volatile and chemically rich than anyone anticipated. It's like finding a gourmet feast in what you thought was an empty pantry. So why is this mix so surprising? For starters, Varuna orbits so far from the Sun that its surface temperature hovers near -230 degrees Celsius, cold enough to freeze air solid. In such extreme cold, simple ices like water and carbon dioxide should dominate. Methane, on the other hand, is a fickle substance. It's prone to vaporizing or breaking down under even slight warmth or sunlight. Yet there it is, clinging to Varuna's surface in significant quantities. This forces a baffling question. How has this methane survived billions of years in the slow bake of cosmic radiation and the occasional weak tug of sunlight? One theory suggests Varuna's methane isn't just sitting there. It's being replenished. Deep beneath the icy crust, reservoirs of liquid or slushy methane could occasionally bubble up through cracks, resurfacing fresh patches before older layers erode away. It's a process we've seen hints of on Pluto and Neptune's moon Triton, where so-called cryovolcanoes spew chilled gases instead of lava. But there's a catch. Varuna's small size and weak gravity make holding onto these volatile gases a challenge. Every eruption would risk losing precious methane to space, like a deflating balloon with no way to refill. Then there's the organic mystery. Mixed in with the methane are darker, carbon-rich compounds, material that looks suspiciously like the building blocks of life. These tarry substances, called tholins, form when methane and nitrogen are zapped by ultraviolet light or cosmic rays, a process that would normally take eons in the frozen quiet of the outer solar system. Their presence implies Varuna's surface has been a cosmic chemistry lab for billions of years, quietly simmering complex molecules under the dim glow of distant stars. But here's the twist: some of these organics appear fresher than they should be. Instead of a uniform, ancient layer, spectral data suggests patchy deposits, areas where these dark materials are concentrated, while other zones remain relatively pristine. That unevenness hints at ongoing activity, as if Varuna isn't just a relic but a world that still tinkers with its own surface. Could seasonal shifts be at work? As Varuna inches closer to the Sun during its elongated orbit, subtle temperature changes might trigger methane frost to sublimate, redistributing organics like a slow-motion paintbrush. Or perhaps buried geysers occasionally belch fresh material, stirring the pot in ways we've yet to imagine. The implications stretch far beyond Varuna itself. If this little world can host such a dynamic mix of ices and organics, what does that say about other Kuiper Belt objects? Could similar chemical factories exist on Sedna, Quaoar, or the countless unnamed worlds lurking in the dark? And if these processes have been running for billions of years, what kind of complex molecules might they have produced? Molecules that, under the right conditions, could someday seed the beginnings of life elsewhere. Varuna's surface isn't just a curiosity. It's a time capsule, a ledger of the solar system's most ancient recipes, and maybe, just maybe, a clue to how the raw ingredients of life get made in the coldest corners of the cosmos. The deeper we look, the more it seems this icy outlier isn't just a passive bystander in the solar system's story. It's an active participant, quietly rewriting the rules of what's possible in the frozen dark. The lack of an atmosphere around Varuna isn't just puzzling, it's borderline contradictory. Here's why. This distant world shares striking similarities with Pluto, another dwarf planet rich in nitrogen, methane, and carbon monoxide, all ingredients known to form thin but detectable atmospheres. Yet while Pluto's tenuous haze regularly creates a shimmering halo around it during telescopic observations, Varuna stubbornly shows no such veil. It's like comparing two seemingly identical flasks, one releasing a faint mist, the other bone dry. Given their comparable sizes and compositions, this glaring absence demands an explanation. So where did Varuna's atmosphere go? The most straightforward answer involves its extreme orbit. Unlike Pluto, which follows a relatively stable path, Varuna's elongated trajectory sends it hurtling from the outer solar system's deep freeze to regions where the sun's faint warmth might briefly, but significantly raise surface temperatures. During these close approaches, any volatile ices on its surface could sublimate, briefly creating a transient atmosphere. But without enough gravity to hold on, those gases would quickly escape into space like steam vanishing from a boiling kettle. Over billions of years, this cycle could have stripped Varuna's primordial atmosphere entirely, leaving behind only the barest traces of gases clinging to its icy crust. But there's a twist. Some models suggest Varuna shouldn't have lost everything. Even Pluto, with its stronger gravity, leaks nitrogen into space at a measurable rate, yet it's retained enough to maintain a seasonal envelope. For Varuna to be completely barren implies something more violent than slow erosion. Enter the impact hypothesis. Imagine a colossal collision early in Varuna's history, one so powerful it not only accelerated the dwarf planet's spin, but also blasted away its nascent atmosphere in a single catastrophic event. This wouldn't be unprecedented. Mars, despite its larger size, likely lost much of its air to a series of giant asteroid strikes, leaving it with just 1% of Earth's atmospheric pressure. Varuna, smaller and more vulnerable, might have been stripped clean in one go. Then there's the wild card, chemical sequestration. Some researchers propose Varuna's missing atmosphere might not have escaped at all, it could be locked away. On ultra-cold worlds, gases like nitrogen and methane don't always behave as expected. Under certain conditions, they can form crystalline structures called clathrates, essentially icy cages that trap and imprison volatile molecules within the crust. If Varuna's interior is riddled with these frosty prisons, its atmosphere might not be gone, just buried, hidden beneath layers of ice like a cosmic secret waiting to thaw. The implications reach beyond Varuna alone. If its atmosphere was truly obliterated by impacts or orbital extremes, that could explain why other mid-sized Kuiper Belt objects lack detectable hazes. Conversely, if the gases are merely locked in icy storage, future observations might catch fleeting whiffs of outgassing during rare orbital alignments. Either scenario forces us to reconsider how delicate the balance is between an atmosphere's birth, endurance, and demise in the solar system's farthest reaches. Varuna's silence isn't just an absence, it's a riddle etched in ice, challenging our assumptions about what it takes for a world to hold onto its sky. Varuna doesn't conform to the neat, spherical mold of most dwarf planets. Instead, the faint glimmers of light reflecting off its surface tell a different story, one of asymmetry, of a world stretched or flattened into something irregular. While objects like Pluto and Eris have enough mass for gravity to sculpt them into near-perfect orbs, Varuna's silhouette suggests a shape more like a cosmic potato, lumpy and uneven. This isn't just an aesthetic oddity, it's a direct challenge to how we understand the formation and evolution of small worlds in the outer solar system. So why hasn't Varuna smoothed itself out? The answer lies in a delicate balance of forces. Gravity, the great sculptor of planets, works tirelessly to pull everything toward the center, erasing imperfections over time. But for gravity to win, an object needs enough mass, and Varuna might be just below the threshold. Estimates place its diameter at roughly 600 kilometers, putting it in a weird middle ground, too small to fully crush itself into a sphere, yet large enough to retain some structural integrity. The result is a fossilized snapshot of chaos, a relic of the violent processes that shaped it billions of years ago. Then there's the rotation factor. Varuna's breakneck spin, completing a full turn every 6 hours, exerts tremendous centrifugal force, flinging material outward at its equator. This could explain why some observations hint at an elongated shape, as if the dwarf planet is being stretched like taffy. But here's the puzzle. Even accounting for its speed, Varuna's irregularity seems exaggerated. That's where the collision theory comes roaring back. A massive impact could have knocked Varuna into its current spin and warped its form, leaving behind a misshapen remnant instead of a clean sphere. The implications ripple outward. If Varuna's shape is indeed a scar from some ancient cataclysm, it suggests the early Kuiper Belt was a demolition derby of colliding protoplanets. This wasn't a serene, orderly place. It was a battleground where worlds clashed, merged, and shattered, leaving behind survivors like Varuna as twisted witnesses. And it's not alone. Other distant objects like Haumea show similar deformations, hinting that whatever happened to Varuna was part of a broader pattern of cosmic violence. Yet the plot thickens when we consider time. Over billions of years, even slight internal warmth from radioactive decay or the slow creep of ice should have allowed Varuna to relax into a more relaxed shape. The fact that it hasn't implies an interior more rigid and cold than expected, as if its very core froze solid eons ago, locking its deformities in place like a fly in amber. This raises a haunting possibility. Varuna might not just be oddly shaped, it could be geologically dead, a frozen monument to the solar system's most tumultuous era. But nature loves exceptions. Some researchers argue Varuna's irregularity might not be ancient at all. What if it's actively maintained by unseen forces? Tidal interactions with a hypothetical moon, long since lost, could have kept its structure unstable. Or perhaps seasonal shifts in surface ices subtly redistribute mass, creating a slow motion wobble that prevents equilibrium. Every new hypothesis peels back another layer, revealing a world far more dynamic and enigmatic than its frozen exterior suggests. In the end, Varuna's shape isn't just a quirk, it's a testament to resilience. A reminder that even in the quietest corners of the solar system, violence and chaos once reigned, and their echoes linger in the twisted forms of the survivors. As we study these distant, misshapen worlds, we're not just mapping ice and rock. We're reading a history written in scars, a story of collisions, spins, and forces that shape the cosmos itself. Varuna defies expectations yet again this time, not with its shape or spin, but with its chill. At first glance, you'd expect a world so far from the sun to be unimaginably cold, and it is, but not in the way scientists calculated. Measurements reveal its surface temperature hovers around -230 degrees Celsius, significantly colder than models predicted for an object of its size and composition. It's as if Varuna has cranked down the thermostat beyond reason, leaving researchers scrambling to explain why. The mystery lies in the mismatch between theory and reality. Most Kuiper Belt objects, even those roughly Varuna's size, retain some residual heat, whether from radioactive decay in their cores or the slow release of energy from their formation billions of years ago. That tiny whisper of warmth should nudge their surface temperatures slightly higher than the surrounding void, but Varuna's readings land closer to the frigid background of space itself, suggesting it's bleeding heat far faster than it should. So where's the missing warmth? One possibility is Varuna's surprisingly dark surface. While distant objects like Pluto and Eris reflect a fair amount of sunlight thanks to bright ice patches, Varuna's terrain seems dominated by darker, carbon-rich materials. These compounds absorb what little solar energy reaches them rather than bouncing it back, acting like a cosmic blacktop that soaks up heat during the day and radiates it away at night. Only in Varuna's case, day is a fleeting concept under the feeble glow of a sun barely brighter than other stars. Without reflective ice to insulate it, the dwarf planet could cool much faster than its neighbors. Then there's the interior question. If Varuna lacks internal heat sources altogether, no radioactive elements generating warmth, no leftover energy from its birth, it would essentially be a dead rock, thermally speaking. But this raises another puzzle. Why would Varuna be so different from similarly sized objects? Some researchers speculate its unusual formation history might hold the key. Imagine a scenario where Varuna wasn't born from the slow clumping of cosmic dust, but from the shattered remains of a larger body. A catastrophic collision could have scattered its original radioactive materials, leaving behind a cooler, inert core stripped of the usual heat-producing elements. But the plot twists when you consider the alternative. Varuna might have internal heat, just not where we can detect it. On icy moons like Enceladus, warmth from deep below percolates upward, creating geysers and cracks on the surface. Varuna's cold exterior could instead hint at a thick, insulating shell of porous ice, trapping whatever meager heat exists far beneath the crust. Picture a thermos bottle in space, freezing on the outside but with secrets simmering below. The implications reach beyond temperature alone. If Varuna truly is this cold, it challenges our understanding of how mid-sized Kuiper Belt objects evolve. Could others share this deep freeze, hiding in plain sight? Or is Varuna a lone outlier, its chill a fingerprint of some forgotten cosmic event? Every new observation peels back another layer, revealing not just answers, but deeper questions about what happens in the shadows at the edge of our solar system. Varuna stands alone, while nearly every other sizable object in the Kuiper Belt, Pluto with its 5 moons, Haumea with its 2, even smaller Orcus with its single tiny companion, boasts at least one gravitational partner, Varuna's orbit remains eerily empty. This absence isn't just unusual, it's statistically improbable. In a region where collisions and captures were once rampant, how could a dwarf planet this large avoid accumulating even a single moon? The answer might rewrite what we know about the chaos of the early solar system. One compelling theory suggests Varuna did have moons but lost them. Picture this: billions of years ago, a massive collision not only warped Varuna's shape and spun it dizzyingly fast but also flung debris into orbit. Over time, the combined effects of solar tides and gravitational nudges from passing objects could have destabilized those moons, sending them careening away into the void. This wouldn't be unprecedented. Neptune's moon Triton, for instance, is a likely captured Kuiper Belt object that may have booted out the planet's original satellites when it arrived. If Varuna suffered a similar upheaval, the evidence would now be lost to time, leaving only its solitary spin as a cryptic clue. But there's a twist. Some researchers argue Varuna's moonlessness might be primordial, that it never had satellites to begin with. Unlike Pluto or Eris, which likely formed in crowded neighborhoods where gravitational dances could easily trap smaller objects, Varuna might have coalesced in isolation, emerging from the solar system's outer fringe as a lone wanderer. Its peculiar orbit supports this idea. While most Kuiper Belt objects follow paths clustered in groups, Varuna's trajectory is a cosmic detour angled steeply away from the common plane. This outlier status hints it could be a refugee from even farther out, a wanderer ejected from some distant, sparsely populated region where moons were rare. Yet the mystery deepens when we consider Varuna's rapid rotation. Fast-spinning objects often owe their speed to past collisions, events violent enough to leave behind moons as debris. If Varuna's spin was caused by a colossal impact, where's the expected orbital aftermath? One possibility is that the impact was so extreme it launched all debris beyond Varuna's feeble gravitational reach, like a shotgun blast scattering pellets into space. Another, more tantalizing idea: what if the moons didn't escape but fell? Over billions of years, tidal forces could have dragged them back down, their orbits decaying until they crashed into Varuna's surface, leaving behind subtle scars now buried under ice. The implications stretch beyond Varuna alone. If moons are missing because of gravitational instability, that suggests the outer solar system was even more chaotic than we thought, with countless small satellites lost to the dark. If they never existed, it challenges our models of how dwarf planets form in different environments. And if they're hiding perhaps as faint, undiscovered flecks of light waiting to be spotted by next-generation telescopes, they could reveal entirely new chapters in the solar system's history. Varuna's loneliness isn't just an oddity. It's a cosmic detective story, one where every blank space in the data is a silent witness to forces we're only beginning to understand. Whether its missing moons were stolen, destroyed, or never born at all, their absence speaks volumes not just about Varuna, but about the turbulent, unforgiving nursery where our solar system's outermost worlds were forged. Varuna's surface tells two stories at once. Some patches gleam like freshly fallen snow, reflecting sunlight with startling efficiency, while others swallow light whole, darker than charcoal. This stark contrast in albedo, the scientific term for how much light a surface bounces back, isn't just a visual oddity. It's a riddle wrapped in ice, hinting at forces reshaping this distant world in ways we're only beginning to decipher. Take the bright regions first. These aren't just random splotches of reflective ice, they're clues. On most Kuiper Belt objects, fresh ice gets dull over time, battered by cosmic rays and micrometeorites into a dingy, less reflective state. So when we spot areas on Varuna that defy this trend, glowing as if they were polished yesterday, it suggests something's renewing them. One possibility: cryovolcanic resurfacing. Imagine plumes of slushy water ice laced with ammonia bursting from beneath the crust, spreading glossy new layers over ancient terrain. We've seen this on moons like Enceladus, where geysers constantly repaint the surface. If Varuna harbors similar activity, even sporadically, it would upend our assumptions about geological vitality in the outer solar system. But the dark patches are even more perplexing. Their spectral signature points to Tholen's complex organic molecules that form when methane and nitrogen get zapped by radiation. These tar-like substances usually take millions of years to accumulate, yet Varuna's dark areas aren't evenly distributed. They cluster in strange, irregular shapes, as if something or someone splattered ink across the ice. That unevenness implies recent activity. Could seasonal shifts be at work? As Varuna inches closer to the Sun during its elongated orbit, subtle temperature changes might trigger methane frost to vaporize in some areas, leaving behind concentrated dark residues like coffee stains after evaporation. Then there's the wild card, impact gardening. Picture cosmic collisions kicking up buried material, exposing darker subsurface layers while scattering bright ice elsewhere. This process could create Varuna's mottled appearance, especially if its interior is stratified like a layered cake with alternating bands of dark organics and pristine ice. Every meteorite strike would then act like a spoon, churning the surface into a patchwork of old and new. But the real enigma lies in the patterns. Some bright and dark regions align with Varuna's equator, while others seem randomly scattered. This lack of symmetry hints at multiple mechanisms at play, maybe cryovolcanism near the poles, impact debris near the equator, and wind-like erosion, yes, even in near-vacuum conditions smoothing certain zones. It's a reminder that Varuna isn't a static museum piece. It's a world with its own weather, its own seasons, and its own slow but relentless ways of changing its skin. The more we study these albedo anomalies, the clearer it becomes. Varuna's surface is a palimpsest. Every bright streak and shadowed valley records a history of violence, renewal, and cosmic chemistry, a history we're only now learning to read. And with each new observation, this distant dwarf planet whispers another piece of its story, challenging us to listen. Names carry weight, especially in astronomy, where celestial bodies often bear titles that echo their most defining traits. So when scientists chose Varuna for this enigmatic dwarf planet, they weren't just picking a label at random. They were invoking a deity as ancient as time itself, one whose myths mirror the planet's own elusive nature. In Hindu cosmology, Varuna reigns as the god of cosmic order, the keeper of celestial waters, and the unseen force binding the universe together. A figure both omnipresent and mysterious, his domain spans the vast oceans and the star-strewn heavens, fitting inspiration for a world that embodies the very essence of the unknown. The parallels between god and planet are striking. Just as Varuna, the deity, governed hidden depths, ruling over everything from monsoon rains to the subterranean rivers of the underworld, Varuna, the dwarf planet, exists in the solar system's shadowy frontier, a place where sunlight is feeble and secrets linger frozen in ice. Both are masters of boundaries. The mythological Varuna guarded the line between sky and sea, while his planetary namesake orbits at the edge of our cosmic map, straddling the known and the uncharted. Even the god's association with unpredictability feels eerily prescient. Centuries before modern telescopes revealed the dwarf planet's erratic spin and puzzling brightness shifts. Ancient texts described Varuna as capricious, his moods as shifting as the tides. But why this name and not another? The International Astronomical Union's naming conventions for Kuiper Belt objects draw from creation myths, particularly those tied to water or primordial chaos. Varuna fit perfectly. Discovered in the year 2000 by astronomers at the Palomar Observatory, the dwarf planet entered the record books during a wave of newfound interest in Hindu and Vedic cosmology among planetary scientists. Where Pluto had been named for the Roman god of the underworld, Varuna offered a different kind of darkness, not just death, but the unfathomable abyss, the deep space equivalent of uncharted waters. There's poetry in the choice, too. Varuna the god didn't just rule water, he was water, an elemental force woven into the fabric of existence. His planetary counterpart, though frozen solid, might still harbor clues to the solar system's watery origins. Some researchers speculate its subsurface could conceal briny liquids, remnants of the ancient ocean that may have once sprawled across the Kuiper Belt. Whether literal or symbolic, the connection transforms the name from mere homage into prophecy, a hint that this distant world, like the deity it honors, holds dominion over secrets deeper than we can yet fathom. Yet the name carries a quiet irony. In Hindu tradition, Varuna's power waned as newer gods rose to prominence, relegating him to the periphery of myth, much like his planetary twin languished for decades in the periphery of our telescopes, overlooked in favor of brighter, closer worlds. Both stand as reminders that some truths don't vanish. They merely wait, half-submerged, for someone willing to look beyond the light. As we probe Varuna's icy shell and untangle its riddles, we're not just studying a dwarf planet. We're resurrecting an ancient dialogue between humanity and the cosmos, one where every discovery feels less like revelation and more like remembrance. Varuna doesn't just exist in the Kuiper Belt, it defies it. This distant dwarf planet orbits in a region crammed with icy remnants from the solar system's birth, yet it stands apart in almost every way. Most Kuiper Belt objects follow predictable patterns, clustering in groups with similar orbits, compositions, and behaviors. Varuna, by contrast, feels like a rebel, a cosmic maverick that refuses to play by the rules. Its wild, tilted orbit, breakneck spin, and baffling surface features set it so far outside the norm that studying it isn't just about adding another entry to the catalogue of icy worlds. It's about rewriting what we thought we knew about the Kuiper Belt's history, and by extension, the chaos of our solar system's infancy. Take its orbit first. While typical Kuiper Belt objects trace gentle, near-circular paths around the Sun, Varuna carves a steep, elongated arc that looks more like a comet's trajectory than a dwarf planet's. This extreme eccentricity suggests it didn't form in place like its neighbors. Instead, it might be an immigrant, a wanderer ejected from some deeper, darker region of the solar system during the planetary chaos of 4 billion years ago. Gravitational tugs from Neptune could have flung it into this peculiar path, but the violence of that journey would have left scars. That would explain Varuna's odd shape, its missing moons, and perhaps even the strange chemistry of its surface. In this light, Varuna isn't just an oddball, it's a forensic witness to the solar system's most turbulent era. Then there's its composition. Most large Kuiper Belt objects like Pluto or Makemake wear thick coats of nitrogen and methane ice, relics of a time when volatile compounds were plentiful in the outer solar system. Varuna has these ices too, but not in the expected proportions. Its surface is a patchwork of extremes, ultra-reflective frost alongside tar-black organics with barely any middle ground. This irregularity hints that Varuna's ices weren't laid down peacefully over eons, but were scrambled by some cataclysm, perhaps the same event that left it spinning like a top. If so, it means the Kuiper Belt wasn't the quiet freezer we once imagined. It was a battleground where worlds collided, shattered, and reformed in ways we're only beginning to grasp. But the real shocker is Varuna's temperature. For an object its size, it's inexplicably cold, colder than models predict, colder than most of its peers. This deep freeze suggests it's not just an inert lump of ice, but a world with an unusual thermal history. Maybe its interior lacks the radioactive elements that keep other dwarf planets faintly warm. Or perhaps its dark surface radiates heat too efficiently, like a cosmic heatsink. Either way, Varuna's chill challenges the assumption that all mid-sized Kuiper Belt objects operate on the same thermodynamic rules. It forces us to ask, was the outer solar system's building material distributed unevenly, with some worlds inheriting more heat-producing elements than others? And if so, what does that say about how planets form in the first place? Here's the bigger picture. Every anomaly in Varuna, its orbit, its spin, its surface, its coldness, isn't just a quirk. It's a clue pointing to a Kuiper Belt far more dynamic and diverse than textbooks describe. If Varuna truly is a refugee from deeper space, it implies the early solar system was a place of drastic migrations, with worlds jostling for position like marbles in a spinning tray. If its chemistry was scrambled by impacts, it means the Kuiper Belt's icy veneer hides a violent past, and if its temperature defies explanation, it suggests our models of planetary formation are still missing critical pieces. That's why Varuna matters. It's not just another frozen rock at the edge of everything. It's a puzzle box waiting to be unlocked. Every new observation peels back another layer, revealing not just answers about this one strange world, but about the forces that shaped all worlds. And in a region where most objects play by the rules, Varuna's defiance might be the key to understanding the rulebook itself. In the cosmic dance of the solar system, most worlds travel with company. Asteroids cluster in families, shattered remnants of ancient collisions still grouped by shared orbits and compositions. Even dwarf planets like Pluto and Haumea have kin smaller objects tracing similar paths, hinting at violent origins that scattered their fragments across space. But Varuna, it orbits entirely alone. Despite decades of searching, astronomers have found no other objects with matching orbits, no siblings born from the same catastrophic event. This isolation isn't just unusual, it's a glaring anomaly that forces us to reconsider everything we thought we knew about how these distant worlds form and fragment. Consider the evidence. When a massive collision shatters a parent body, the debris typically stays gravitationally linked, creating what scientists call a collisional family. These groups share nearly identical orbital traits, like the remnants of the asteroid Vesta in the inner solar system or Haumea's distant icy kin in the Kuiper Belt. Yet Varuna's orbit remains a singularity, with no known objects following its steep, elongated path. This absence raises two unsettling possibilities. Either Varuna never suffered the kind of impact that creates families, or something erased all traces of its kin long ago. The first scenario challenges our understanding of the early Kuiper Belt. If Varuna avoided catastrophic collisions while similarly sized neighbors like Haumea didn't, it implies the outer solar system's violence was patchy, some regions devastated by impacts, others eerily untouched. This would require a delicate balance of conditions, like Varuna forming in a sparsely populated zone where collisions were rare. But that seems unlikely given current models, which paint the young Kuiper Belt as a demolition derby of icy protoplanets. The second scenario is even more intriguing. What if Varuna did have siblings, but they were stolen? Simulations suggest Neptune's gravity could have scattered collisional families over billions of years, flinging some members into wildly different orbits while ejecting others entirely. The trouble is, we'd still expect to find a few survivors, yet Varuna's orbit remains a solo act, unless the destruction was total. A particularly violent impact might have pulverized Varuna's family into dust too fine to detect, or accelerated fragments beyond the sun's grasp entirely. Imagine a cosmic bullet shattering not just its target, but the very evidence of the crime. There's a third, darker possibility lurking in the data. Varuna might not be from here at all. Its extreme orbital tilt and eccentricity hint it could be an interloper, captured from the fringes of the solar system or even another star's lost debris. In this light, its isolation isn't a mystery, it's a passport stamp, proof of an epic journey across interstellar space. While rare, such wanderers aren't unheard of. The asteroid Oumuamua famously passed through our solar system in 2017, a visitor from parts unknown. If Varuna shares that exotic pedigree, its missing family might still be out there, drifting in the darkness between stars. The implications ripple outward. If collisional families can vanish so completely, our census of the early solar system might be riddled with gaps, entire chapters erased by time and gravity. Alternatively, if Varuna truly formed alone, it challenges the idea that all dwarf planets were shaped by violence, suggesting some worlds emerged intact from the primordial cloud. Either way, its solitude speaks volumes not just about its own past, but about the fragility of cosmic evidence and how easily the universe buries its secrets. What makes Varuna's loneliness so profound isn't just the absence of companions, but the questions it leaves hanging. Are we looking at a survivor of unimaginable destruction or a traveler from beyond? A world that never knew kin or one that outlived them all? Until we find more of its kind or confirm their irreversible loss, Varuna will remain the solar system's most enigmatic orphan, a silent testament to the forces that build and break worlds in the dark. Beneath Varuna's icy shell, there may be forces stirring, not with fiery magma, but with something just as strange: cryovolcanism. The eruption of slushy ice and frozen gases instead of molten rock has been spotted on moons like Enceladus and Triton. But Varuna, it's so cold, so distant, that the idea of any geological activity seems absurd. And yet, telltale clues hint this frozen world might not be as dormant as it appears. The evidence is subtle but compelling. Telescope observations reveal patches of ultra-bright terrain, regions where fresh ice gleams as if recently exposed. On most inert worlds, cosmic radiation would have dulled these spots to a uniform gray over billions of years. Their persistence suggests something, or someone, is scouring Varuna's surface clean, like a cosmic Zamboni resurfacing a ring. Then there's the uneven distribution of methane. Unlike Pluto, where this volatile gas blankets the surface evenly, Varuna's methane clumps in odd concentrations, as if belched from discrete vents rather than diffusing naturally. But how could cryovolcanism work in such extreme cold? The answer lies in antifreeze. Ammonia, mixed with water ice deep beneath Varuna's crust, could lower the freezing point of subsurface oceans to -100 degrees Celsius, still chilly by Earth standards, but warm enough to keep slush flowing in the Kuiper Belt's perpetual winter. Add a dash of salts or methanol, and you've got a brine capable of oozing through cracks, building pressure, and eventually erupting in slow-motion geysers. These wouldn't be the dramatic plumes of Enceladus, but something quieter: icy slurries seeping through fractures, freezing almost instantly in the void, leaving behind glossy new plains. Yet the real surprise isn't the how, it's the why. Most active icy worlds owe their energy to tidal flexing, the gravitational kneading they endure from nearby planets. Varuna has no such giant neighbor to stretch its core. Instead, its heat might come from within. Radioactive decay from trace elements like potassium or thorium could provide just enough warmth to keep its interior malleable. Or perhaps Varuna retains primordial heat from its violent birth, a fossil furnace banked beneath miles of ice, still simmering after 4 billion years. Either scenario would make it one of the smallest known bodies with ongoing geology, defying expectations for a world its size. The implications are staggering. If Varuna's cryovolcanoes are real, they'd confirm that even the solar system's frozen outliers can harbor dynamic interiors, places where chemistry, not just temperature, dictates behavior. More tantalizingly, these briny eruptions could ferry organic molecules from deep underground to the surface, creating pockets of prebiotic soup in the coldest reaches of space. It's a reminder that activity isn't the sole domain of planets and moons. Sometimes the quietest worlds are the ones with the most to say. Varuna's surface isn't just a static canvas, it's a shifting mosaic of color, changing in ways that defy simple explanation. While most distant objects in the Kuiper Belt appear as featureless dots through telescopes, Varuna reveals something far more dynamic. Observations over the past 2 decades show subtle but measurable shifts in its hue, drifting between pale blues, faint reds, and neutral grays like a cosmic mood ring. These variations aren't random noise in the data. They follow loose patterns that hint at hidden processes reshaping this frozen world. The most straightforward explanation points to cosmic radiation, the relentless bombardment of high-energy particles from the Sun and distant galaxies. Over time, this radiation can chemically alter surface ices, breaking apart methane molecules and reassembling them into complex organic compounds called tholins. These tar-like substances tend to appear reddish, which might explain why Varuna's darker regions skew toward warmer tones. But here's the catch: radiation darkening usually happens over millions of years, not decades. For Varuna's colors to shift on human timescales suggests something else is at play, accelerating or interrupting the process. That's where seasonal changes enter the picture. Despite its staggering distance from the Sun, Varuna's elongated orbit creates slight variations in temperature and solar exposure. At its closest approach, weak sunlight might briefly warm certain regions enough to vaporize surface frost, exposing darker underlayers or triggering chemical reactions. As it retreats, those areas could refreeze, creating fresh, bright patches. Think of it like a slow-motion tide, where the ebb and flow of heat subtly repaints the landscape over centuries. This would mirror phenomena seen on Pluto, where seasonal shifts redistribute nitrogen ice across its surface in sprawling, ever-changing glaciers. Yet the plot thickens when you consider the unevenness of these color shifts. Some regions appear to darken faster than others, as if Varuna's surface reacts more intensely in specific zones. One possibility is that impact craters or cryovolcanic vents act as hotspots, funneling gases or altering local chemistry in ways that amplify discoloration. Another theory involves Varuna's rapid spin. Its 6-hour rotation might create temperature extremes between day and night sides, driving frost to migrate from warmer to cooler areas. Over time, this could create a patchwork of fresh and weathered terrain, each with distinct reflective properties, but the wildest hypothesis involves something far more active: transient atmospheres. On dwarf planets like Pluto, seasonal warming can briefly sublimate surface ices into a thin, temporary gas envelope. If Varuna experiences similar micro-outbursts, even on a smaller scale, these fleeting atmospheres might redistribute colored particles across its surface like a celestial airbrush. Picture plumes of reddish tholins lifted by weak winds, settling in new patterns before vanishing back into the ice. While no direct evidence confirms this yet, it would elegantly explain why some color changes appear both rapid and localized. What makes these shifts so compelling isn't just the mystery of their cause, it's what they reveal about Varuna's hidden vitality. A world this remote should be frozen in time, its surface locked in stasis. Instead, it flickers, evolves, and responds to its environment in ways that blur the line between geology and meteorology. Every new observation peels back another layer, showing us a place where even the faintest sunlight can rewrite the rules, and where the slow dance of chemistry paints the ice in colors we're only beginning to decode. Varuna doesn't just carry secrets, it carries scars. Every anomaly in its orbit, spin, and composition whispers of a time when the solar system was a battlefield, where planets didn't just form but fought for survival. The most compelling theory ties Varuna's strangeness to the Great Planetary Migration, a chaotic reshuffling 4 billion years ago when gas giants like Neptune rampaged outward, bulldozing everything in their path. As Neptune moved, its gravity would have acted like a cosmic wrecking ball, hurling smaller objects like Varuna into skewed, stretched orbits while others were ejected entirely. This could explain why Varuna's path looks so violently out of place. It's not an original resident of the Kuiper Belt, but a refugee flung here during the solar system's most turbulent era. But there's a twist. Varuna's orbit isn't just eccentric, it's clustered. Along with a handful of other distant objects, its trajectory angles steeply away from the main plane of the solar system, as if something invisible is herding them. This peculiar alignment has fueled speculation about Planet 9, a hypothetical giant world lurking beyond Neptune that could be gravitationally shepherding these outliers into their strange configurations. If real, Planet 9's tug might not just explain Varuna's orbit, it could also account for why this dwarf planet spins so fast. A close encounter with a massive, unseen neighbor could have imparted that dizzying rotation, like a billiard ball struck off-center. Yet the most tantalizing clue lies in Varuna's surface chemistry. Its mix of methane, nitrogen, and organic sludge mirrors materials found on comets, relics of the solar system's primordial building blocks. Unlike Pluto, where geological activity has recycled these ices over eons, Varuna's composition feels frozen in time, a snapshot of the raw ingredients that existed before planets took shape. This raises a startling possibility. Varuna might not be a fractured fragment of a larger world, but a nearly intact survivor from the solar system's infancy, one of the few left unprocessed by later collisions or internal heating. The implications ripple across astronomy. If Varuna truly is a preserved artifact from the planetary migration era, studying it could reveal what the original Kuiper Belt looked like before Neptune's upheaval. Its erratic spin becomes a fossil record of ancient gravitational encounters. Its missing atmosphere hints at how volatile compounds were stripped away during violent orbital changes. Even its loneliness, the absence of sibling objects, might not be an accident, but evidence of how thoroughly the migration event cleared its neighborhood. But the real revelation lies in the unfinished story. Varuna's oddities don't just point backward, they hint at forces still at work. If Planet 9 exists, its gravity could still be tweaking Varuna's orbit today, making this distant world both a relic and an active participant in the solar system's slow dance. Every new observation peels back another layer, revealing not just where Varuna came from, but how the cosmos continues to shape it, one cryptic clue at a time. Varuna remains frustratingly out of focus, not because it's inherently blurry, but because we've never gotten a good look at it. Every scrap of data we have comes from fuzzy telescope snapshots taken across billions of miles of space. It's like trying to decipher a billboard through a snowstorm. While missions like New Horizons gave us stunning close-ups of Pluto and Arrokoth, Varuna has never been visited by a spacecraft. That absence isn't just an inconvenience, it's the reason so many of its mysteries persist, locked behind the limitations of remote observation. Consider the challenge. Even our most powerful ground-based telescopes struggle to resolve Varuna's shape, let alone surface details. Its brightness fluctuations hint at dramatic terrain, but is that ruggedness from craters, cryovolcanoes, or something else entirely? Without direct imaging, we're left piecing together clues from indirect methods like watching a shadow puppet show and trying to reconstruct the hands casting the shapes. Spectroscopy, which analyzes light reflected off Varuna's surface, reveals tantalizing chemical signatures, but these readings are often muddled by noise. A methane patch might indicate cryovolcanic activity or just an ancient impact that dredged up buried ice. The uncertainty fuels debates that only a closer look could settle. This is where next-generation tools like the James Webb Space Telescope could change everything. Webb's infrared capabilities might pierce through the noise, mapping Varuna's surface chemistry in unprecedented detail. Imagine pinpointing not just that methane exists, but where it's concentrated, whether in sprawling plains or localized geyser-like vents. Thermal imaging could hunt for heat anomalies, betraying hidden cryovolcanic hotspots or subsurface slush. Even Varuna's temperature discrepancies might finally make sense if Webb detects unexpected warmth radiating from certain regions, but telescopes, no matter how advanced, have limits. What Varuna truly needs is a visitor. Picture a dedicated mission, a small, nimble probe like New Horizons but optimized for the Kuiper Belt's outer reaches. Equipped with high-resolution cameras, ice-penetrating radar, and particle analyzers, it could answer questions we haven't even thought to ask. Does Varuna have hidden fault lines from ancient impacts? Are there trace gases hovering just above its surface, too tenuous for Earth-based detection? Even a flyby lasting mere hours could revolutionize our understanding, transforming Varuna from a pixelated enigma into a world with geology, weather, and history. The irony is palpable. Here we are, an era where rovers traverse Mars and probes dive through Saturn's rings, yet Varuna, a world that defies so many expectations, remains just beyond our grasp. Its distance is no excuse. The Voyager probes reached interstellar space, and New Horizons crossed the Kuiper Belt on a shoestring budget. The real barrier isn't technology or even distance, it's prioritization. Every unexplored world like Varuna represents a gap in our cosmic story, a missing page in the solar system's autobiography. The push for a mission isn't just about satisfying curiosity. Varuna's quirks, its orbit, its spin, its surface aren't isolated oddities. They're threads in a larger tapestry, clues about how dwarf planets form, evolve, and interact in the solar system's farthest reaches. Solving its mysteries could rewrite textbooks, revealing whether our models of planetary migration, ice chemistry, and even the Kuiper Belt's violent past hold water. Until then, Varuna will keep its secrets, a faint dot in the darkness reminding us how much lies left to explore. Varuna's density shouldn't be this confusing. For a world we've studied for over 2 decades, pinning down how much mass is packed into its icy frame ought to be straightforward. But the numbers tell a different story, one where estimates swing wildly, leaving scientists divided over whether Varuna is a lightweight snowball, a dense rocky core wrapped in ice, or something far more exotic hiding beneath the surface. Take the low-end estimates first. Some calculations suggest Varuna's density hovers around 0.9 grams per cubic centimeter, lighter than water ice. If accurate, this would imply a world barely held together, a cosmic rubble pile with more empty space than solid material. Picture a loosely packed snowball, its interior riddled with gaps and fractures, porous enough to crumble in your hands if it weren't for gravity's faint grip. This interpretation aligns with Varuna's rapid spin. A fragile, low-density structure could flex and compress without tearing apart, explaining how it withstands its dizzying rotation. But then there's the opposing data. Other measurements push Varuna's density closer to 2 grams per cubic centimeter, nearly double the initial guess. At that range, we're no longer talking about a fragile ice ball. Instead, Varuna might harbor a significant rocky core, buried beneath miles of ice like a frozen peanut with a dense, mineral-rich center. This would mirror larger dwarf planets like Pluto, where gravity has sorted heavier elements inward over billions of years. If Varuna fits this mold, it challenges assumptions about how objects in the Kuiper Belt formed, suggesting some worlds accreted more rock than we thought possible in the outer solar system's icy outskirts. The plot thickens when you consider the middle ground. Some researchers propose Varuna's density could land somewhere in between, around 1.5 grams per cubic centimeter, a value that splits the difference but raises new questions. At this range, the dwarf planet might not be uniformly porous or rocky, but layered like a cosmic onion. Imagine a brittle, icy shell encasing a denser, slushy mantle, with perhaps a smattering of rock mixed in. This hybrid model could reconcile conflicting observations, explaining why some measurements hint at lightness while others suggest heft. It also opens the door to something even more intriguing: hidden liquids. On icy moons like Europa, the combination of moderate density and internal heat creates subsurface oceans. Could Varuna, against all odds, host similar briny pockets beneath its crust? The implications spiral outward. If Varuna is porous, it reshapes our understanding of how mid-sized Kuiper Belt objects endure over billions of years. A loosely packed structure would make it more vulnerable to collisions, yet here it is intact, suggesting the outer solar system might be gentler than we thought. If it's dense and rocky, it hints at a chaotic past where building materials weren't as neatly sorted by distance from the sun, with heavy elements scattered farther out than models predict. And if it's layered with potential liquids lurking inside, it forces us to reconsider where we look for habitable environments in the solar system. The real frustration and fascination lies in the uncertainty. Without a spacecraft visit, Varuna's density remains a riddle wrapped in ice, each interpretation pointing to a radically different vision of this distant world. Is it a fragile relic, a dense anomaly, or a dark horse in the search for extraterrestrial liquids? For now, the numbers whisper, but they don't speak clearly. And that's the paradox. The harder we look, the more Varuna refuses to fit into any single box. Varuna doesn't just orbit the sun, it staggers, its axis tilted so dramatically that its seasons unfold like a cosmic pendulum swing. While Earth's relatively gentle tilt gives us predictable winters and summers, Varuna's axial lean is so extreme that entire hemispheres might spend decades drenched in perpetual sunlight before plunging into centuries of frigid darkness. Picture a world where the very concept of a day loses meaning, where the sun doesn't rise and set but crawls along the horizon for lifetimes before vanishing for eras. This isn't just seasonal change, it's geological time made manifest, a slow-motion dance of light and shadow sculpting an alien landscape. The mechanics are mind-bending. Varuna's axial tilt, estimated at over 60 degrees, nearly triple Earth's, means its poles, not its equator, often point directly at the sun during solstices. At these extremes, one polar region could bask in unbroken solar glow for decades, while the other languishes in an endless night so deep it makes Arctic winters seem fleeting. But here's the twist. Varuna's orbit is so stretched that its distance from the sun varies wildly, amplifying these seasonal quirks. During its closest approach, feeble sunlight might briefly nudge temperatures high enough to vaporize surface ices, creating fleeting atmospheres or triggering frost geysers. Farther out, that same sunlight dwindles to a spark, leaving Varuna to freeze into near absolute stillness. Now imagine the surface transformations. A patch of methane ice under decades of relentless sunlight wouldn't just sublimate, it might chemically mutate, breaking down into reddish tholins that stain the terrain like cosmic rust. Meanwhile, shadows could preserve ancient ice deposits in permanent cold traps, creating reservoirs of volatiles untouched for millennia. Over centuries, these processes would etch Varuna's face into a palimpsest of light and dark, with fresh frost painting bright streaks in some areas while others darken under eons of radiation. It's a world where geology moves at the pace of empires rising and falling, where a single season could outlast human civilization, the wild card Varuna's spin. Its rapid rotation, once every 6 hours, means that even during polar day, surface temperatures would yo-yo violently between brief, weak warmth and bitter cold. The result could be a surreal hybrid of seasons, sprawling ice fields that crack and shift under the strain of thermal expansion, or nitrogen geysers that erupt in sunlit zones only to freeze mid-plume as darkness returns. For hypothetical explorers, it would be like standing on a giant, wobbling top, where the horizon tilts dizzyingly and the sun's path scribes erratic loops across the sky. Yet the most profound mystery isn't how these seasons unfold, it's what they leave behind. On Earth, seasonal cycles recycle materials predictably. Water evaporates, falls, and flows. But Varuna's epochs-long variations could lock away volatiles in icy vaults for ages, only to unleash them in sudden, dramatic outbursts. A reservoir of nitrogen frozen solid for 10,000 years might explosively sublimate when sunlight finally reaches it, creating temporary atmosphere pockets or carving gullies in the crust. These aren't weather patterns, they're geological upheavals disguised as seasons, rewriting the surface in fits and starts. What makes Varuna's rhythms so mesmerizing is how they defy intuition. We're accustomed to seasons measured in months, driven by a stable orbit and modest tilt. Varuna's cycles operate on timescales so vast they blur the line between climate and cosmology, where a single summer could outlast all recorded human history, and winter's grip lingers like an ice age stretched to infinity. Studying them isn't just about puzzling out another world's weather. It's a glimpse into how time itself shapes planets, and a humbling reminder that the universe operates on clocks we're only beginning to read. The silence from Varuna is deafening. While some dwarf planets like Pluto emit faint but detectable radio waves, hints of magnetic fields or subsurface activity, Varuna broadcasts nothing but radio silence. This absence isn't just an observation gap, it's a profound enigma. A world this large with such puzzling traits should theoretically hum with some electromagnetic whisper. But our most sensitive instruments hear only void. The question isn't just whether Varuna is hiding something, it's whether the silence itself is the clue. First, consider what radio emissions usually signify. On geologically active worlds, moving liquids like subsurface oceans or molten cores can generate magnetic fields. These fields interact with solar wind, creating radio waves detectable across interstellar distances. Even frigid Pluto emits sporadic bursts, likely from slushy interactions beneath its icy shell. Varuna, though, sits mute. One explanation is brutally simple. Its core might be stone-cold dead. Without internal heat to churn conductive fluids, no magnetic dynamo forms and no signals rise to the surface. This would align with Varuna's abnormally low temperature, suggesting a world that burned out its radioactive fuel long ago, leaving behind a frozen, inert husk. But there's another possibility, one that turns the silence into intrigue. What if Varuna's core is active, but in ways our tools can't perceive? Earth's instruments are calibrated for certain frequencies and strengths, fine-tuned to objects closer and more energetic than a distant dwarf planet. Varuna's emissions might pulse at frequencies too low or too weak for our arrays to catch, like a radio station broadcasting just outside the dial. Alternatively, its magnetic field could be trapped beneath an unusually thick ice shell, unable to propagate into space. Picture a submarine's sonar pings muffled under polar ice present, but imperceptible from the surface. The wild card, Varuna's composition. If its interior lacks metals like iron common drivers of magnetic activity, any internal motion might produce fields too feeble to detect. This wouldn't mean Varuna is lifeless. Even a sluggish, metal-poor core could host slow convection, maybe even sustaining hidden liquid layers. Compare it to Jupiter's moon Callisto. No detected magnetic field, yet evidence suggests a subsurface ocean persists. Varuna's silence might not be absence, just a different language we haven't learned to hear. The implications stretch beyond instrumentation. If Varuna is truly inert, it challenges assumptions about how mid-sized Kuiper Belt objects age. Why did it cool faster than Pluto? Was its core stripped of heat, producing elements during a catastrophic collision? Conversely, if the silence is an illusion, a limitation of our technology, it hints at undiscovered forms of planetary activity, processes subtle enough to slip beneath our observational radar. Both scenarios force us to reconsider what active even means in the frozen fringes of the solar system. For now, Varuna's radio silence stands as both a challenge and a taunt. It dares us to build better detectors, to listen more closely, to question whether the universe's quietest voices might be the ones worth straining to hear. Until then, the void speaks volumes, not in what it says, but in what we're missing. Varuna might not have always been alone. One of the most provocative theories about this enigmatic world suggests it was once part of a cosmic duo, a binary dwarf planet system where two icy bodies orbited each other before some cataclysm tore them apart. This isn't just wild speculation, it's a hypothesis born from Varuna's strangest quirks. Its rapid spin, irregular shape, and peculiar orbit all fit the aftermath of a violent separation, like a ghostly fingerprint left behind after a celestial partner vanished into the dark. The evidence starts with Varuna's rotation. Spinning once every 6 hours is absurdly fast for an object its size unless something gave it a dramatic kick. A binary system's gravitational dance could explain that speed. Imagine two dwarf planets circling each other, their mutual tug creating a stable rhythm. Then, a close encounter with Neptune or another massive object disrupts their orbit, sending one spinning away while the other is ejected entirely. The remaining partner, Varuna, would inherit an exaggerated rotation, its axis wobbling from the sudden loss of counterbalance. This scenario mirrors what we see in asteroid binaries, where collisions or gravitational theft often leave survivors with bizarre spins. Then there's the orbit. Varuna's path is steeply inclined and stretched, deviating wildly from the Kuiper Belt's orderly plane. If it once had a twin, their shared center of mass would have followed a different trajectory than either individual object. A sudden split could have flung Varuna onto its current eccentric path, like a slingshot releasing one stone while the other sails off in another direction. Curiously, other oddballs in the Kuiper Belt, like the dwarf planet Haumea and its scattered family, hint at similar violent histories, suggesting binary breakups weren't rare in the early solar system's chaos. But the most tantalizing clue lies in what's missing. Binaries often leave debris behind rings, moons, or dust trails, yet Varuna's orbit is eerily clean. Unless the separation was so catastrophic that both objects were flung into radically different trajectories, leaving no trace of their partnership, some models suggest Varuna's hypothetical twin could have been hurled into interstellar space, becoming a rogue dwarf planet drifting between stars. Others propose it might still be out there, hiding in the Kuiper Belt's gloom, its orbit now so altered that we haven't connected the dots. Not all scientists are convinced, though. Critics argue that Varuna's traits could stem from a single massive impact rather than a binary divorce. A direct hit from another large object might have imparted the same spin and orbital weirdness without requiring a lost sibling. Plus, binaries tend to form in specific conditions, usually where gentle collisions allow two bodies to gravitationally capture each other. Varuna's chaotic neighborhood might have been too violent for such delicate partnerships to survive long. Yet the binary theory persists because it elegantly ties together multiple mysteries. A twin could explain Varuna's absent moons, their orbits destabilized during the split. It might account for the dwarf planet's lopsided shape, sculpted by tidal forces during its partnered days. And it offers a reason for Varuna's unusually reflective patches, fresh ice exposed when the separation ripped apart its crust, like a scab torn away to reveal gleaming skin beneath. The implications stretch beyond Varuna alone. If binaries were once common in the Kuiper Belt, their shattered remnants could litter the outer solar system, each a silent witness to forgotten alliances. Some researchers even speculate that Planet 9, the hypothetical giant world thought to shepherd odd orbits, might itself be the runaway half of a primordial binary, its gravitational echo still nudging former partners like Varuna into uneasy paths. For now, the theory remains open, a tantalizing what-if hovering at the edge of our knowledge. Whether Varuna's twin is lost to the void or never existed at all, the possibility forces us to see this distant world not as an isolated oddity, but as a potential survivor of something grander, a broken piece of a partnership that once defined the early solar system's wild, untamed youth. Varuna's wild, lopsided orbit looks like the aftermath of a cosmic wrestling match, and Neptune might be the heavyweight champion that threw it off balance. The giant planet's gravitational pull is a defining force in the Kuiper Belt, sculpting the paths of countless icy bodies over billions of years. But Varuna's extreme trajectory, so stretched and tilted it resembles a comet more than a dwarf planet, pushes the limits of what Neptune's influence should realistically explain. Untangling this gravitational tug-of-war isn't just about orbital mechanics. It's a forensic investigation into the solar system's most chaotic era. Start with the basics. Neptune's migration during the solar system's infancy was anything but gentle. As the planet inched outward, its gravity slingshotted smaller objects into bizarre orbits, a process known as mean motion resonance. Some, like Pluto, got trapped in stable, rhythmic dances with Neptune, completing exactly 2 orbits for every 3 of the giants. Others were hurled into the scattered disk, a repository of eccentric orbits at the Kuiper Belt's fringe. Varuna's path, however, defies easy categorization. Its steep orbital inclination, tilted nearly 30 degrees from the solar system's plane, suggests it didn't just get a nudge from Neptune. It might have been body-slammed. The challenge lies in the numbers. modern simulations can recreate Neptune's migration and its gravitational fallout with startling accuracy, but Varuna's orbit consistently breaks these models. Most scattered Kuiper Belt objects follow predictable patterns, their eccentricities and tilts clustering around values explained by Neptune's influence. Varuna, though, veers into statistical outliers. Its orbit is so extreme that some researchers argue it required additional forces, perhaps a close encounter with another massive object during Neptune's upheaval, or even the hypothetical pull of Planet 9. Imagine a game of pinball where Neptune flips the first flipper, but something else, an unseen hand, lands the final, decisive blow. Yet the plot thickens when you consider timing. Neptune's migration likely happened within the solar system's first 100 million years. If Varuna was indeed scattered during this period, it's had over 4 billion years to slowly erode its orbital quirks through subtle gravitational nudges from passing stars or galactic tides. The fact that its oddities persist hints at either a more recent disruption or an orbit so stable in its instability that it's found a precarious balance. This paradox, a path that feels both violently altered and eerily resilient, makes Varuna a living contradiction, a world that shouldn't exist in its current form, yet undeniably does. The stakes are higher than just one dwarf planet's past. If Neptune alone can't explain Varuna's orbit, it implies gaps in our understanding of the outer solar system's evolution. Were there more planets involved in the early chaos, their gravity stirring the pot before vanishing into the dark? Or does Varuna's path preserve the fingerprint of a younger, more turbulent Kuiper Belt, one where collisions and close calls were even more rampant than we thought? Every failed simulation, every orbital anomaly, is a whisper from an era when the solar system wasn't the orderly clockwork we see today, but a demolition derby of worlds in flux. For now, Varuna's dance with Neptune remains an open question, one part celestial mechanics, one part detective story. The clues are there, etched in the angles and arcs of its motion, but the full truth might require something we don't yet have, a glimpse of the solar system's birth through a lens we haven't yet invented. Until then, this distant world spins on, a silent testament to forces that shape not just its own path, but the very edges of our cosmic neighborhood. Varuna's dark stains tell a story older than life itself. Those tar-like patches aren't just cosmetic flaws, they're complex organic molecules called tholins, carbon-rich compounds that form when methane and nitrogen endure eons of cosmic radiation. But here's the twist: these aren't mere leftovers from the solar system's birth. They're evidence of an ongoing chemical laboratory where simple ingredients simmer into complexity under the dim glow of distant stars. The real question isn't whether Varuna has organics, it's whether they're ancient relics frozen in time, or signs of a world still tinkering with life's building blocks. Start with the primordial scenario. If Varuna's tholins date back 4 billion years, they'd be snapshots of the solar system's raw ingredients, preserved like bugs in amber. Picture methane ice on young Varuna getting zapped by ultraviolet light from the infant sun, each photon knitting carbon atoms into ever more intricate chains. Over millennia, these reactions could have produced everything from simple hydrocarbons to amino acids, the same compounds that, on Earth, eventually sparked life. The allure here is the purity. Unlike planets bathed in liquid water or scorched by volcanoes, Varuna's deep freeze might have kept these molecules pristine, uncontaminated by later geological upheavals. They'd be cosmic time capsules, offering a glimpse into the probiotic soup that existed before life took hold anywhere. But the plot thickens when you consider the alternative: active chemistry. Varuna's organics aren't uniformly distributed. They cluster in odd concentrations, like spilled ink on a notebook. This irregularity suggests ongoing processes, perhaps seasonal methane geysers spewing fresh material onto the surface, where radiation then cooks it into new compounds. Imagine a slow-motion fountain, each eruption spraying volatile gases into the void, only for them to freeze, darken, and accumulate in drifts. If true, Varuna isn't just a museum of ancient chemistry. It's a working lab, still running experiments in how complex organics arise in the absence of warmth or liquid water. The astrobiological implications are staggering. On icy moons like Enceladus, subsurface oceans mix water with organics, creating environments where life could emerge. Varuna lacks that liquid, but what if it doesn't need it? Some lab studies show that under extreme cold and radiation, simple organics can form membranous structures resembling primitive cells, no water required. These azotosomes might not be alive, but they demonstrate how far probiotic chemistry can go without Earth-like conditions. Varuna's dark patches could harbor similar surprises, molecules nearing the threshold of complexity, frozen mid-assembly like half-built machines. Yet the ultimate mystery lies in delivery. Even if Varuna's organics never sparked life locally, they might have seeded it elsewhere. Comets and asteroids routinely shuttle material between worlds, and a single impact could have ejected Varuna's carbon-rich fragments toward the inner solar system. Picture a snowball loaded with tholins smashing into early Earth, its payload dissolving into warm tidal pools where millennia later the first microbes stirred. It's a haunting thought. The dark stains on this distant dwarf planet could be distant relatives of the chemistry coursing through your veins right now. What makes Varuna's organics so compelling isn't just their existence, it's their duality. They're both artifact and process, relic and reactor. They challenge us to expand our definition of habitable beyond liquid water and sunlight, to consider the silent, frozen places where life's ingredients assemble in the dark. Whether these molecules are ancient or newborn, they whisper the same tantalizing possibility. The universe might be building life's puzzle pieces everywhere, even in the coldest corners of the Kuiper Belt, on worlds we've barely begun to understand. Varuna's frozen exterior hides a tantalizing possibility, one that defies logic at first glance. Beneath miles of ancient ice, this distant dwarf planet might cradle a secret, a subsurface ocean kept liquid by forces we're only beginning to understand. The idea sounds absurd for a world so far from the sun, where temperatures should render even the deepest layers rigid. Yet the clues, however faint, point to something stirring in the dark. Start with Varuna's density. Some estimates suggest a value around 1.5 grams per cubic centimeter, too low for a purely rocky body, but curiously heavy for a simple ice ball. This middle ground hints at stratification, a dense core wrapped in lighter ice with potential gaps in between. Picture a cosmic jawbreaker, its layers separated by briny liquids that act as lubricants, allowing the icy shell to shift independently of the interior. It's not pure speculation. Moons like Europa and Enceladus taught us that radioactive decay or tidal flexing can generate enough heat to maintain underground seas, even in the solar system's freezer. Then there's the chemistry. Varuna's surface boasts methane and nitrogen volatiles that shouldn't stick around for billions of years without replenishment. If cryovolcanic vents occasionally breach the crust, spewing fresh material onto the surface, what's driving them? A subsurface ocean could provide the pressure and material, acting like a buried reservoir that occasionally bubbles over. Even more telling, the uneven distribution of these compounds. If Varuna's liquids are localized, pooling in pockets rather than forming a global sea, they might explain why some regions appear geologically refreshed while others look weathered and old. But the real wild card is ammonia. Traces of this antifreeze, if mixed with water beneath Varuna's shell, could lower the freezing point to -100 degrees Celsius. Add salts or methanol, and the ocean's survival becomes plausible. On Earth, brine remains liquid in polar ice caves at similarly extreme temperatures. Varuna's ocean wouldn't be a churning, blue expanse, more like a sludgy, supercooled aquifer, oozing between layers of ice under immense pressure. proving this wouldn't require a landing. A future flyby mission equipped with a magnetometer could detect conductive fluids by their interaction with solar wind. Seismic sensors might listen for ice quakes, their echoes revealing liquid pockets like sonar mapping submarine trenches. Even subtle gravitational anomalies could betray the ocean's presence, tugging at orbiting probes in telltale ways. The implications are staggering. If Varuna, small, cold, and isolated, harbors liquid water, it redefines the habitable zone's boundaries. Life, at least in theory, wouldn't need sunlight or a thick atmosphere, just chemistry, time, and a hidden sea whispering in the dark. Varuna's secrets won't reveal themselves, we'll have to go and pry them loose. While telescopes and simulations have given us glimpses, the only way to truly crack this dwarf planet's code is to send a mission, slicing through the 4 billion miles of void that separate us from its frozen surface. The good news, we're closer than ever to making that happen. The bad news, every option comes with staggering challenges, from brutal distances to power constraints that make Pluto's visit look like a weekend getaway. First up, the flyby. Think of this as a cosmic drive by shooting a high-speed dash past Varuna, cameras snapping furiously, sensors gulping down data before the spacecraft vanishes back into the dark. New Horizons proved it's possible, zipping past Pluto and Arakoth with breathtaking precision. But Varuna's orbit adds a cruel twist. Its elongated path means timing is everything. Launch too early or too late, and you'll miss the window by decades. Even with perfect alignment, the journey could take 15 to 20 years using current propulsion. That's a generation of scientists waiting for a handful of hours at closest approach. Yet the payoff could rewrite textbooks. A flyby's cameras might finally resolve Varuna's shape, settling the rubble pile debate, while spectrometers map surface chemistry in detail, revealing whether those dark patches are fresh organics or ancient scars. But why stop at a flyby? Imagine an orbiter looping Varuna for years like Cassini did Saturn. The hurdles here are brutal. Slowing down requires fuel or risky aerobraking in an atmosphere that might not even exist. But the rewards, unmatched. Continuous monitoring could track seasonal changes, catch cryovolcanic eruptions, or even sniff out trace gases escaping from hidden oceans. An orbiter's radar might pierce the ice, hunting for liquid layers beneath, while laser altimeters chart topography down to the meter. The catch: power. Solar energy is useless this far out. We'd need advanced nuclear batteries like those on Perseverance, but scaled for decades of deep space loneliness. Then there's the Holy Grail, a lander. Picture a probe touching down on Varuna's frost-crusted surface, drills spinning, sensors tasting the ice for clues about its origins. The engineering nightmares multiply here. How do you anchor to a world where gravity is barely a whisper? How do you survive temperatures that make Antarctic winters feel balmy? One concept involves harpoons and ice screws, latching onto the terrain like a mountaineer clinging to a glacier. Power becomes even trickier. Without sunlight or compact nuclear options, a lander might rely on short-lived radioisotope heaters, its lifespan measured in weeks rather than years. But those weeks could revolutionize astrobiology. A mass spectrometer could dissect tholins molecule by molecule, hunting for amino acids or other precursors to life. Seismometers might feel the groan of shifting ice, betraying the ocean beneath. So why pour billions into chasing these ghosts? Because Varuna isn't just another ice ball, it's a time machine. Its bizarre orbit preserves traces of the solar system's violent adolescence, while its surface chemistry could hold blueprints for how life's ingredients assemble in the dark. Solving its riddles would recalibrate our search for habitable worlds, proving that dynamism exists even in the frozen fringe. The clock is ticking. With every passing year, Varuna retreats along its eccentric path, growing fainter and colder. The window for a manageable mission won't stay open forever, but when we finally go, whether with a fleeting flyby or a daring lander, we won't just be visiting a dwarf planet. We'll be stepping into the unknown, hunting for answers that could redefine our place in the cosmos. And if history's any guide, the universe's quietest corners often shout the loudest truths. Varuna isn't just another icy relic. It's a vault, a frozen archive preserving secrets from the solar system's most chaotic era. While planets like Earth and Mars have been reshaped by volcanoes, oceans, and erosion, Varuna's surface has lingered in deep space stasis for billions of years, its craters and chemistry untouched by the forces that rewrite geology elsewhere. This isn't merely old ice, it's a snapshot of a time when the solar system was still assembling itself, a window into the raw ingredients that built worlds like ours. Every anomaly, the skewed orbit, the erratic spin, the patches of primordial sludge isn't just a puzzle. It's a clue to how planetary diversity emerges from cosmic chaos. Consider what Varuna lacks: the geological churn that recycled Earth's crust, the atmospheric weathering that sandblasted Mars's surface, even the cryovolcanic resurfacing that keeps Pluto young. Its stillness is its superpower, the methane staining its ice. That could be the same methane that swirled in the solar nebula before the sun's first light. The lopsided shape, a fossilized imprint of collisions that once shaped every protoplanet, erased elsewhere by time. Even Varuna's loneliness, its missing family of fragments, hints at a lost chapter when the Kuiper Belt was a battlefield, not a graveyard. While other dwarf planets bear scars smoothed by eons, Varuna's wounds remain fresh, its history written in ice too cold to heal. Yet the true revelation isn't just about Varuna, it's about the solar system's hidden diversity. This dwarf planet defies categorization, straddling the line between comet and world, its traits blurring the boundaries we've drawn around planetary formation. Why do some ice giants develop oceans and atmospheres while others, like Varuna, freeze solid? Is its weirdness a fluke or proof that our models of planetary birth are missing critical variables? The answers could rewrite the story of how small worlds evolve, revealing that chance cataclysmic impacts, near misses with giants, even the luck of chemical mixtures plays as much a role as physics in shaping planets. And then there's the existential layer. Varuna's survival makes it more than a time capsule, it's a counterfactual. What if Earth had formed farther out, its water locked in ice, its geology stillborn? What if Jupiter's migration had scattered our cradle of life into the dark? This distant world forces us to confront how fragile our own planet's story might be, how narrow the path between a living world and a frozen fossil. Its silence isn't emptiness, it's a mirror reflecting back the unlikeliness of everything we take for granted. The irony is profound. In our rush to explore Mars's canyons or Europa's oceans, we nearly overlook the quiet witness at the edge of everything. Varuna doesn't dazzle with geysers or glaciers. Its magic is subtler, a testament to preservation, a reminder that some truths aren't found in dynamism, but in patience in the rare places where time itself seems to hesitate, holding its breath for us to catch up. From its breakneck spin to its bizarre orbit, from the missing atmosphere to the eerie radio silence, Varuna isn't just a single mystery. It's a tapestry of 25 enigmas, each one pulling us deeper into the unknown. This distant dwarf planet defies every expectation, spinning faster than it should, colder than it ought to be, and shaped by forces we're still struggling to name. Its surface flickers with unexplained brightness shifts, its composition hints at ancient organics, and its lonely orbit stands as a silent challenge to our models of how the solar system formed. Every answer we think we found only unspools more questions, turning Varuna into more than just a world, it's a frontier, a place where the rules of planetary science seem to bend and blur. What makes these mysteries so thrilling isn't just their strangeness, it's what they represent. Varuna is a living laboratory, a frozen time capsule holding clues to the solar system's most violent, formative moments. Its erratic path could rewrite the story of Neptune's migration. Its missing moons might reveal how collisions shaped the early Kuiper Belt. Even its radio silence speaks volumes, forcing us to reconsider what active really means in the farthest reaches of space. This isn't just about one oddball dwarf planet. It's about the bigger picture, the untold chapters of how worlds are born, evolve, and sometimes defy categorization entirely. But here's the real magic. Varuna's story isn't finished. Every telescope pointed its way, every algorithm sifting through its faint light, brings us closer to breakthroughs we can't yet imagine. Will we find evidence of that hidden ocean? Will a future mission catch cryovolcanos in the act? Or will the next discovery be something entirely unexpected, a curveball that sends us back to the drawing board? That's the beauty of exploration. The universe always has another card up its sleeve. So stay curious, follow the missions, support the science, and never stop asking, what if? Maybe you'll be the one to crack Varuna's code, spotting a pattern everyone else missed. Drop your wildest theories in the comments. Could Planet 9 be tugging at it? Are those dark patches more than just organic sludge? The conversation doesn't end here, because out there, 4 billion miles away, a tiny world is spinning secrets into the void, waiting for us to listen. And the moment we do, the solar system might just make a little more sense. Until then, keep looking up.